Bismillahirrahmanirrahim. Assalamu alaikum students. This is Imran Sikandar and we are going to start with centroids and center of gravity, and these notes I have already distributed on my Google Classroom, and I have already basically been explained to you in my theoretical classes of during the classroom normal classes of our NAD. So here I'm just going to explain you further so that you can gain more in-depth knowledge about this subject of centroid and center of gravity, which is, I've told you, is more related to, it's a mathematical, under mathematical domains, and the reason being that you won't be applying directly your engineering statics knowledge to it, but it will be more mathematical concerning how will you understand differentiation and integration. Okay, so first of all, if you see, we can see that importance of the center of the gravity is that stability is very important whenever you're designing mechanical structures, mechanical components, and its position is very important, because if you do not design a stable structure, as forces are applied or once the loading changes, it can result in catastrophic failures. For example, in case of this ship, you can see what is happening here is that it has just basically toppled over. The reason being that it's having a basically center of buoyancy is below the center of gravity. So if you look at this, is a very important point. Its center of gravity is below the center of gravity. That is the main reason it has basically toppled. So these things are very important. If centroid and center of gravity, same with you. This aeroplane, if you look at it, how basically you can the type of loading, if you see over here, is that it has got three different types of axis over here, and that is one is basically the, if you look at it, one of it is the pitch axis. If you look at it, this is the roll axis, the other one is the pitch axis, and it has also got is yaw axis. Three different types of axis. So you can see that it has got various types of controls. Like over here, if you look at it, at this thing, there is basically what is called as the rudders acting. Then these are the stabilizers. Here you can see the ailerons. So the different systems works on these roll axis, pitch axis, and the yaw axis. If basically any type of variable loading is being applied, and basically some mechanism or mechanical functions fails to exist. For example, in case of a rudder, that if the steel cables break or the hydraulic cables undergo some failure, there is leakage of fluid or something like that, so the aeroplane cannot be remain stable and can crash. It can basically go down with lot of precious lives. Same is with, if you look at it here, in case of your double decker. Yeah, if you look at this as your double decker, if you go to London especially, or you go to European states or anything countries, you will see that these double deckers are very common. And the reason being is that, but once you start traveling in it, the driver is always going to tell you to go sit in the lower seats until they are filled up. The reason being that as more and more passengers goes above the center of gravity, and the weight of the bus starts to increase, and basically that can basically cause some instability by as its center of gravity will be raised. Another thing is that these racing cars, if you look at it, they are basically very flat. If you look at it, they are very flat, and their base is very close to the ground. The reason is being then that when they basically becomes because of these two things, they becomes more stable, and because of that greater stability, when they are basically turning the corners, especially those round curves like this, are very sharp corners, something like this. When they do it, when they do at high speeds, they are able to maintain their stability, and they will not topple down because of those high centrifugal forces. Otherwise, they can just go out of this arc, and you have seen a lot of video and crash with the side side basically walls. So that is resulting in life failures. Okay, and if you look at it, let's go to the next slide. If you look at here, uh, sports physics is very important in this slide also. uh, Increasing again, you people might have be doing some sort of bodybuilding or something like that. You can see whenever someone is lifting these heavy loads, he has to he has to increase the base area to lower the center of gravity to balance the weight. This swimmer, if you look at it, he basically pushes the center of gravity outside his body in order to maintain a greater thrust and greater when he's basically diving in the swimming pool. And same with this sprinter is basically, if you look at it, he's aligning his body, uh, aligns the center of gravity with the rib cage, which helps him attaining more initial speed. If we go to the next slide, applications include the dynamics of the rigid bodies, calculation of moment of inertia, orbital mechanics, aircraft safety, and astronomy, calculations, very important, biomechanics, then structural members, it is very important. Okay, so like in if you look at it, for dynamics of rigid bodies, the calculation of moment of inertia is very important. As you know that this moment of inertia is basically a property of the structure in which is a function of mass and radius. Okay, this is the main property. It depends upon basically, and it depends upon the basically the mass distribution of the structure and the geometry. So moment of inertia is basically resistance to angular acceleration or deceleration of the body. Okay, and for whenever basically you calculate the moment of inertia for any body, you need to calculate very accurately the center of gravity is very important. So this center of gravity is very important here to calculate basically the moment of inertia of the body. If CG is not calculated accurately, you will always be able to find your moment of inertia will not be calculated in a right way. So this is very important. If you look at it, then basically motion of planets, very important, orbital mechanics. As you know, the scientists always predict the mass of the moon and different planets, and by predicting their uh, weight of the planets, they can predict various astronomical properties of the planets. Aircraft safety, as I told you about just recently, it depends upon various mechanical functions to stay stable in the when it is flying. And structural members, calculation of moment of area and is very important. Moment of area, actually it is the second moment of area. So if you look at it, it is the second, not to be precise, it is the second moment of area, uh, and which is defined as the resistance to bending. Okay, so it basically, if you look at it, this moment of inertia is basically equals to second moment of moment of inertia is equals to I. If we will see these formulas, is equals to, I think so, mr square, and this second moment of area is basically also equals to, for any axis, if you look at it, it will be say, you can say I is equals to y square dA. You can say Ix is equals to, and similarly Iy is equals to x square dA. So this is very close terms we use a lot in mechanical engineering, and whenever we concerned with dynamics, if you look at it, for dynamics we will be using moment of inertia. For dynamics we will be using moment of inertia, and for statics and solid mechanics, in statics and solid mechanics, we'll be using this term, this moment of area, second moment of area, a lot. So this is well, let's go to the next slide. If you look at it, for the next slide, center of gravity, center of mass, and the centroid of the body. So each and every particle, as you know, you are very much familiar with these terminologies. Center of gravity is a geometrical center of body, center of mass at which the whole mass of the body acts, and centroid is the geometrical center of the body. You know these definitions since long when you are in metric or your O levels. Okay, so each and every particle in body has a differential weight dW. If you look at it, each and every particle in the body has a differential weight. If you look at it, it has a differential weight dW. Okay, and the result of all these infinite parallel forces dW is termed as the weight of the body. Okay, so if you look at it, all these bodies, if you sum up all these differential weights, you will be ending up with what is called as this, the total weight of the body. Okay, and again, these are not geometrically shaped bodies; these are arbitrary shaped bodies. Okay, so if you look at it, here are three terms that you really have to basically tackle, and that is, if you like, if you go here, like if you look at it, this is x bar, y bar, z bar. These are the centroidal coordinates of the body. These are very important whenever you're considering the weight or centroid. So if you see centroid is here, it will always be represented by x bar. You must always remember this, y bar and the z bar. But there is another one which is over here, is that if you go here, it is x bar, x tilde, y tilde, and this is z tilde. If you look at it, these are x tilde, y tilde, and z. These are the basically the local coordinates. Okay, are basically, we will treat it as local coordinates. Okay, it has local coordinates. These are the local coordinates. Okay, every body is compared, like for example, if this body is here, and it will have lot of these local coordinates. Like here, if you look at it, it will have, you can say here, one local coordinate. It is made up of infinite coordinates. Here also, here also, here also, here also. You can say there are infinite number of these local values. Like this is dW. You can say this is dW. Then this is dW1, dW2, dW3, dW4, dW5, dW6. Okay. So there it is composed of a lot of these uh, basically individual dWs. Okay, and dW1, dW2, dW3, D4, lot of this. And basically we want basically to not this dW1, dW, we want to have the total weight of the body, which is W, and which must be acting at the centroid. So how basically, but if you look at it, this axis x, y, and z, if you look at these axis x, y, and z, the weight is basically this dW weight. If you look at it, it is acting along the z tilde axis. It is acting along the z tilde axis. And if you look at it here also, this overall weight W is acting along the z bar axis, and it has some finite distances along these respective three-dimensional axes, which is x, y, and z, and its distance along the basically perpendicular distances along the y-axis is x bar, and along the y-axis is going to be x bar for its moments to be calculated. Okay, so if I say that what will be this distance of, for example, if you look at it, here we have, if you sum the various forces, and if you look at it, let's make it a bit. If you look at it, here we have basically we sum the moments about the different axes. For example, if we have got this weight acting downwards of this total weight of the body, and it is acting along the z axis here, and you can say this is the weight which is acting along the z axis, we can make it instead of this, we can say this is the weight, this is the weight which is acting along the, this is your weight W along the z-axis, and if you look at it and this is, if you look at it, this is the weight acting along the, differential weight acting along the z-axis. This is the weight acting along the z-axis. This is the weight acting along the, which is dw. Okay, here what was w. Okay, now this weight, if you look at it, if we multiply this weight along the, what is called as the x tilde, if you multiply it with this along the x tilde, this dw multiplied with this x tilde, the dw is along the z-axis and this x tilde is basically along the x-axis. So vertical weight dw z-axis and momentum is x bar. So what are we going to get here is basically, if you look at it, we will be getting what is called as the moment about the y-axis. And if we sum up all these moments, because it's an arbitrary shaped body, you remember I have told you we'll use integration, and if we sum up all these weights, here it was like dw, dw1, dw2, dw3, d4, w4, all these, if we sum up together, we can use what is called as the basically summation signs. Okay, we can basically sum up summation of all the moments about the y-axis. Okay, and if we go here also for this, if we say like it was this. Now on the contrary, if we go again for this dw, and basically this dw which is acting over here, and its moment along the y-axis, its moment along the y tilde, you can say y tilde. So y tilde along this was y tilde, this y tilde along the dw. dw is basically along the z, and y tilde is basically along the y-axis. So z into y will give you basically a moment about the, it will be giving you a moment about the x-axis, remember, and here we will be getting the moment about the y-axis. One will, this will be my, and this moment will be moment about the x-axis. Okay, and a similar way, in order to calculate the moment about the z-axis, if you look at it, what have they done here is that they have rotated the body about the z-axis. They have rotated this body, just make it more clear, and here they have rotated the body about 90 degrees about the z-axis, and once they have rotated it about this is now your new z-axis. This is the now the weight is acting along the uh, x-axis, and we want basically the, along the this dw will acted upon by the z head, which is basically this thing along this if you want here, because as you rotated it, so it will be giving you movement about the basically what is called as the moment about the z-axis. Okay, so here like it was this, if before that if you look at it, this one was about summation of moments about the x-axis, and the last one will give us, this one will be giving us the moment about the, it will be giving about the moment, it will be giving about the moment about summation of all the moments about the z-axis. It will be giving the moments about the z-axis. Okay, so this way. But so actually, if you, another thing over here, if you look at it, this thing is that this this thing, this what we have here is this x bar w. If you just take this example, we know that this w is equals to integral of dw. This w is equals to integral of dw. So in place of w I can write, because if we sum all these internal differential weights dw, what we were getting this w. So when we integrate this dw, we get w. So in place of w, we can write it as x bar integral of w. So here we are always interested, I told you, in what we are interested, always in the x bar of the body. We are always interested in calculating the x bar of the body, And since we are calculating in x bar of the body, from here if we divide this integral of dw, we will get x bar, and this is the formula, that is for x bar equals to integral of, here it was integral of x tilde dw over integral of dw will give you the centroid of this arbitrary shaped body. Same with the y bar, same with the z bar. Okay, so in this way you basically calculate the centroid of the arbitrary shaped bodies. Now we basically, if you look at it, we go to the next slide, and it is better if we just make it a bit more smaller to understand it much better. Center of mass is point at which the whole center of the mass of the body acts. If you look at it, this is the center of mass point at which the whole mass of the body acts. Okay, so in just to in the old way, in the previous slides we were having x tilde basically times the dw. Okay, now here since we know it was dw, but we know very well that if you look at it here, what is w? W is nothing but equals to m times g. So instead of for dw, it for dw, what will happen? It will happen dw will be equals to dm times of g. You can write it like this. So the same here, what they have done is instead of w, they have put it as dm times of g. But g is constant on the numerator, and at denominator it's a universal constant, so it gets cancelled. You can utilize it, and so the result of when center of mass is considered for this body, the main formula that we're going to use is going to be this one. X bar will be equals to x tilde dm over integral dm. Same with y bar, same with z bar, very easy. And remember one thing, that the center of mass and the center of gravity will always coincides when the gravity field is uniform. Okay, which means it will always coinciding when the gravity field is uniform in the body. It will only vary if the body is under basically weightlessness. So which means that the how because g is a constant here, but we are saying if you have heard these things studied in inter, it will called as variation of g with altitude. With altitude, you have done it in inter physics first year, I think. In the same way, g will also vary as a function of depth, as a function of depth when it's going at the core of the earth, or it can be also be vary, g will always be varying as a function of height, like the body is going in space, as a function of height. Okay, this is h. Please, I'm doing my writing, please it's a bit more shabby. I'll try to make it more better. Okay, so this is being done, and in the same way I have told you that the for all bodies, the center of mass and g will always be coinciding when the gravity field of that body is uniform. Okay, and the other thing is that what is centroid? It is the geometrical center of the body. So it basically, what is telling you over here is the point about which uh, so it depends upon which the volume or area is equally distributed. So main thing is, when centroid is saying, we're talking about volume and area. And another thing here is, what we're doing is, we're saying that the density of the material dm is constant. We're saying the density is constant. So mass, since density equals to mass per unit volume, so mass dm will be equals to root times of dv. So we can have this formula here is x bar equals to x tilde dv over integral of dv, y bar equals to integral of y tilde dv, and z bar equals to z tilde into dv. So what they have done, in place of dm, we can replace it with rho dv, and density is constant. So we can apply this formulas. As over here I told you, the density is always going to be constant. But just imagine a body in which you can just here a case scenario is there. As we have told you, the center of mass and centroid will always be constant when gravity is uniform. If we have a body here, if we have a body slightly, okay, so let us say we have a rectangular body here. This is the body. So if this body is made up of one simple material, say it is made up of aluminium, okay, so it's when we say it is made up of one different material, so we can say its center of mass and its centroid will always coincide. Center of mass and centroid will always coincide, not center of gravity but center of mass and centroid. And if it is of a geometrical shape, same material, its center of gravity will also coincide. Okay, but another scenario is here that if this body, again the same body is there here, if we go, we have this body, and if you look at it, we have this axis here, vertical axis. So the top is made up of, say, aluminium, and the bottom is made up of, say, steel. Now in this unique scenario, remember one thing, its geometrical center, will always be, centroid is geometrical center of body, at its where the two axes meets. So its centroid will be here at C, but its center of mass will shift downwards. Its center of mass will shift downwards. Why? Because the density of steel is greater than that of aluminium. Okay, so if you put like any material which is of more denser than steel, then the density can, the center of mass can go on the upper side also, but it will not coincide with the centroid. So these things are very important in understanding how basically structures in various components and structures, because remember this thing, that this section that I'm talking about can be a beam of your home, can be beam of your structure, it can be anything like this, because if this is a rectangular structure that I told you, okay, it will always have another third dimension like this. Okay, so we are just talking about this cross section, but actually we are dealing with the whole beam. Okay, whether it's your home, it's the beam of a bridge, it can be a truss, it can be a mechanical structure, it can be the beam of your truck, of your automotive car. So different kinds of beams are almost everywhere. You just think in your mind and you will have a beam as an example. Okay, so another very important thing which is with just for knowledgeable thing, extra knowledge to gain, is that please forgive, my work is a bit more shabby. I'll try to make it more better, as I'm just doing it for the first time as well as with this tablet and pen tablet. So let's basically get more knowledge of this subject by seeing this picture. If you look at it, this picture, that if you have got, just look at this cone. If you look at this cone is basically not a two-dimensional one, but it's a three-dimensional structure. Like here you have X, you can see you have X and you have Y and you have Z in this. Okay, so but for these type of structures you need basically volume, because cone is 3D structures, you need volume. For volume, basically if you look at it, they have taken a disk as an element in order to represent dV, because if you look at it, if you look at a disk is basically uh, if you look at it, it's basically a cylinder. A disk is basically a cylinder. If you look at it, this disk, if it's a finite disk, it will be like a cylinder. Okay, it will have some area. You can say pi r square. Pi r square will be the area, and this will be the height h. It will be the height h. So we can replace this disk in our basically cone. And if you look at it, I can tell you the centroid of this disk will have the two coordinates, as I can very easily say, is that x bar will be and 0 for this centroid, and y bar will also be 0. If I'm You can say x bar will be 0 and z is on the top, so I will not say this, but I will say z bar will also be equal to 0, but it will have some finite value in y bar which we need to calculate, maybe any value 4, 5, 6, 3, any value. But why? Because it will not have any centroidal coordinates along the x and z bar. It will be 0, but it will all basically its the y bar of this will vary along the y axis, and which we will basically do in the numericals coming ahead, how to calculate the centroid of three-dimensional 3D element, 3D structures, and cone is basically considered as a 3D structure. If you look at it, if you have structures in which you have got like uh, basically one symmetric axis, like for example, if you come here and you see you have one structure here, a beam, then you have got another beam, and you can say you have got a very large thing. So if you look at this structure, it will have its centroid. It's not symmetric about the. If you look at it, this is my one of the axis here is basically going to be the y-axis, and this is going to be the x-axis. If you look at it, its centroid will basically lie somewhere along the y-axis. It will lie somewhere along the y-axis, its centroid. This is my y-axis. But if you have a beam like this, in which it has got, if I cut it along the y-axis or I-axis, it will permit perfect symmetry. A volume will be equally displaced along the y-axis, or if I cut it along the x-axis, so its a centroid will meet where the two symmetry, where the two axes coincides, which means the y-axis and x-axis coinciding at this point, it will have its centroid over here. Okay, if we have got uh, if for example, then we can have also structures in which like if you got a ring, a wearing ring, finger ring, its centroid will lies in space exactly at the middle. So in this way you can predict the centroids of various components and various structures. Okay, so if we go to the next slide, if we go to the next slide, okay, like till now we were doing integration for these bodies. We were using integration signs, but remember one thing: if we have got composite bodies are dealing with 3D volumes, okay, and the bodies are what is called as the perfect geometrical shapes, which we called it in engineering as the bodies are primitives. They are primitives. Now, what is primitives? Primitives, as the name suggests, very old and historic. You can see if you go to I don't know, at Teen Talwar or Do Talwar, there is Sean circle over here. You can see on the Sean circle they have placed all the primitives like the cylinder, the square, the cone, the toroid, uh, and basically the hemisphere. These are all basically it comes under domain of primitives. When dealing with these type of structures, we use the same formula if you look at it. But to be precisely speaking, if you look at it, instead of integral sign, we are using a summation sign in all these things. Because of this regular geometric shape if comes, we do not want to use the integral signs, we will use the summation signs. So here it is. Integration sign can therefore be changed to summation signs because we have basically got composite bodies which are made up of various primitives or various components, like the in case this case, if you look at it, it has got this is this. If you look at it, this is what is this component, the top one. This is the cylinder. If you sorry, this is the I'm sorry, this is the cone. This is the cone. This is cone, and what is this one? This is cylinder, and what is this? This is a hemisphere. This is the hemisphere. Half of the sphere is hemisphere. So these composites, when combined together, we can calculate their centroids, but it is more easier because we would just using the summation sign instead of the integral. The reason being they are perfect geometrical structures, so we can replace the integral sign with the summation sign, and we can do it for the areas also, for areas and for volumes for the centroidal calculations. And if you look at it, and if same thing, just for further knowledge, we can say, like center of mass and centroid. You're talking you about, uh, like here in case you can calculate. So just for extra knowledge, let to tell you that. Basically, we have done chapter 4, in which we have done uniform distributed loading, and basically that loading was expressed in pounds per inch or newtons per meter. That is for the line distribution of any structure. Okay, the line distribution, and there are two more loadings that you will be doing in your future assignments. It will be areal distribution loadings and volume distribution loadings. For areal distribution loadings, it will be area means pressure. It will be pressure loadings, and for volume it will be basically like Newton per cubic meter. It will be volume loadings. Its examples could be seen here just for knowledge. This is line loading. This is the pressure loading. If you look at it for a dam, if you see, the pressure is continuously increasing as we go. You already know this one. This is like omega into some sort of a function. This is we haven't done it. You will do it in fluid mechanics, this type of loadings. You can see as you go along the reach to the depth of this dam, this is water all around. This is pressure loading, and this pressure loading, as you go at the bottom, just to let you know, pressure is a function of height, so the depth increases as you go down. This is the volume loading. Here is we have a steel cantilever beam of very heavy weight, so basically it will apply for this structure, apply volume loadings. Okay, so just centroid, center of mass and center of gravity here. uh, Again, same technique that I have told you about here is that they have explained to you that with similar components, for a volume components, we will using the same formula, x bar equals to x dww. They're not using tilde, just to make life easy for you. Okay, and another thing which is very important is that just for your knowledge, I'm trying to tell you, is that this thing what is called as the uh, this x dw and y dw are termed as the first moment of areas of the body. They are termed as the first moment of areas. We can replace this dw with, again I've told you know the technique, w goes to mg, so dw goes to gdm, and they have replaced it as x integral x dm upon m. And here again, this is x is actually x tilde, y tilde, these are the local, and this is the centroidal coordinates. We're doing out all along with JL Mariam and Craig this book. Okay, and so these are the formulas just for you some extra knowledge, that if you want to read, you can read here also in this book, which is I have already uploaded on my drive. uh, if you want to further enhance your knowledge of this subject of center of mass, because that we are doing all from the RC Hibbler. So I hope you would have understand the initial fundamental concepts of this centroid, center of mass and center of gravity. So we shall proceed with numericals in the next lecture. Again, thank you to everyone, and I shall see you soon. Jazakallah. Allah Hafiz.